So, to derive the magnetic field of a ring, which he could just randomly throw in there, I mean, it's your professor this year, it's kind of weird. Generally, they show this in class, and they don't ask you to derive it. But, like I said, you could be given this as a valid application of the Beat-Savart law. It's nothing wrong with it. It's just that they usually present it instead of giving it as an exam question. So, okay, what do you do to solve this? Well, remember, you got to fill up this guy. So we got to find all these components that are needed here. Now, the fact that this is a ring makes this a little bit easy for us because it seems symmetric. Whatever you see below the axis, you see above the axis, which drives me to pick DLs symmetrically about here. I'm not going to be dumb though and put the DLs in spots where I cannot easily see the angles that I'm forming with the ring. I'm going to pick the DLs in a smart way. What's a smart way? As the current is going around the ring, there's going to be a point that it drives itself into the page and out of the page. Let's say right now that right here it dives again out of the page, sorry, rather. And it dives into the page here. The direction of the current, all it does is flip the sign of the magnetic field direction. So I'm just going to make it go, I don't know, like this way for now. It's going to dive into the page at that spot, go behind the page here, and then it's going to come back up and rise right there. It's going to face directly out of the page. These are going to be my DL elements that I'm going to choose symmetrically about this ring. Each one can be connected right now to the point P that you see on the right. So take this to be the z-axis. Obviously, P can be placed here anywhere you want. Okay, so we call its position Z. Why Z? Because that's the z-axis, and that's your distance from the xy plane here. Why not call it Z, right? So call this little guy Z. If you called him Z naught, if you called him George, it's still the same thing. But I like to call them a coordinate variable because I want to indicate to myself that I control that variable right now. I get to pick the point wherever I want. So surely I connect the DLs with P because that will give rise to the R vector. Here's my R vector. Now, this one, just to show you the difference with the previous one, I will do it with symmetry. Again, you don't have to. If you don't, this one does become very complicated because it has three components, unfortunately, and not only one like the other one. I would have a dbx, dby, and dbz. The dbx and dby integrals would vanish, but good luck showing that. You know, it would take. It's an effort. You know, it's an effort. So, okay, here's the drill. DL is pointing out of the page right now. So remember, the direction of the magnetic field, the simple direction, is given by this cross product. Thumb along DL then, index along R. You can open your arm on the right so you can do that more easily. So thumb outside behind you, point behind you, and then turn your fist a little bit so that it points toward the ground. You should be seeing a middle finger that goes up into the right now. Something like this. And it's no coincidence. With Jeffrey, I think with Neo as well, I introduced this topic and I told you that these two vectors define a plane together. You can kind of see that plane right now, you know, and how the magnetic field is actually the normal vector to that plane. But that's not important now. Just know that dB is perpendicular to both DL and R. Perpendicular, you say, that means that's this angle over here is 90. Okay, we keep it going. So what's next? If you do the same thing with the other one, you can imagine by symmetry, if you literally flip this vertically right now, okay, you can see where it will go. If you flip it vertically, sorry, it will go like this. And it's perpendicular again to this r vector that points to the point P. It's supposed to be. So that's 90 as well. If you collapse the dB down, it has components to it. So you have over here, I call these the planar components. They contain both an x and a y. It's hard to see it right now, but if I did another cross section, you would be able to. They don't matter though, because they're going to cancel anyways. At any given time, they go opposite to each other. So they don't matter. But just know that they are not just one component. They contain a mix of x and y. So out they go. Equal and opposite at any point of the integral. But the one that's not equal and opposite is the dBz right now, as you can see. That survives. So for the dBz, 90 here, we can decide how we're going to place the angles, but just notice one second. If I call this angle theta right now, you know, a lot of people want to be going opposite here like this and calling this theta. I used to do this a lot when I was more young and innocent. Don't do that. They're not exactly opposite. In fact, you want to do this. The whole angle is 180 or pi. So as you can see, the remnant over here, this remnant, will be 180 minus 90 minus theta. Minus 90 minus theta, like that. So that will give you just 90 minus theta. That's it. That is what this angle is. And then, since this angle is 90, you can conclude that the top one over there is actually theta right now in the big triangle. So be careful about that. It's a thing that always got me when I was deriving this in the much earlier past. So, I'm not going to get the full dB. It seems I'm only going to get dBz. And dBz can be expressed in terms of dB, as dB is the hypotenuse here. So using theta, this is adjacent, this is hypotenuse, cosine is the relationship here. Here's where it gets even more interesting. Notice that this is magnitude, while this over here, upstairs, has direction. This is one of the few times where you can work out the Biot-Savart law without the cross product. The magnitude of a cross product, you know it from Linalge. It is the size of the first vector, the size of the second vector, but you know, typically when you do this, this is the unit vector r, and this is r squared, obviously. So the size of dl is just dl. The size of r hat is literally 1. And then the sine of the angle between them, we will call it sine of gamma. So gamma is the angle between r hat and dl. We will see what that is in a second. Underneath, the situation hasn't changed. Notice there are no unit vectors because this is now magnitude. Yeah, so that's how you can go about converting the dB element into its magnitude. You can just take the magnitude of the cross product and you're done. All right. So I'm filling in. This is going to be playing the role of dB right now. So I'm missing a few things. I know that dB is this. What the heck is cos theta right now? If you look at the big diagram, cos theta is this guy over that guy. So I can write it down. Cos theta is adjacent over hypotenuse. Sure thing. All right. What's next? Well, what would be curly r? Curly r would be Pythagoras. you can go and do square root of r squared plus z squared, like that. Okay, and you can put that here. All good. So far, so good. Just collecting the tools. What about DL? For the DL, you might want to take a top view to see it better. Okay, your little DL here. If you take a top view, obviously you're just going to see a circle, and you're going to see the XY plane. So the top view here shows you a little circle. That's how the ring looks. And let's pretend that DL was taken to be here and there, if we look at it from a top view. So this is DL. Okay. I want you to see that you can find it using polars again. You know the radius of the ring in this problem. It's like R or A sometimes, whatever they give you. So if you use polar coordinates, this guy's R, and this opening angle is a small azimuthal angle change, d phi. So there goes the L. It is R d phi, and since it's counterclockwise, it is in the phi hat direction. Nice. That's how you get dl. We only want the size, though. We don't care about the direction, so omit the direction. Now, we got to think a little bit about that sine gamma thing. The heck is that? Well, it's kind of hard to convince you here, but I'll try. See, if you have the ring like this, and the r vector elevates itself like this above the ring and goes toward the point P, no matter where you take it, it's always going to be perpendicular to the ring right now. And I can show you how that works. So for example, there's the 90 angle here, and then it's like skewed over here. It's kind of hard to draw, but it would be like, like this. Same thing over here, skewed like that. Can you see again that at any given point, our little DL, the ring represents the DL right now because it's along it. Okay? It's along that ring. And we can see that the ring with the R vector makes always a 90-degree angle, no matter what. In fact, the gamma here is 90 throughout the actual integration, throughout where you take this. You're always perpendicular to that surface of the ring. Okay, fair. The geometry is like a birthday party hat. That's what it reminds me of. It literally looks like a birthday party hat. So you can try, if you draw a line on the birthday party hat, you can try and see that whatever line you draw on it to go to the tip, it's going to be perpendicular to the circle at the base. By the way, that's why it's called a right circular cone. Because no matter what line you draw over here to go to the P, it's going to make a 90-degree angle with a circle at the bottom. Right circular cone. You learn something every day, eh? So the sine of gamma over here, it's just sine of 90, and of course that is 1. I think it's time we put everything back together. So I'll start at this level. Here's dBz. I'm going to start on the right. I'm going to put dB in afterwards. So that's going to be dB over here. Cos theta, I'm going to fill it in with what it is right there. And then I keep going. For a second, I'm going to collect terms. So I got mu naught I, let's see here, over 4 pi sine of gamma All right. And then R dl over curly R cubed. Well, I go one step further now. I know what dl is. I know what R is. So it's debatable though if I want to use, I'm thinking if I want to use Cartesians at this point. Probably do, to be honest with you. Debatable. So I'm gonna replace all these. Sine gamma, I want to remind you, was 1 for you. So we get mu naught I R over 4 pi multiplying 1. dl was R d phi from the 2D diagram. And then we have R cubed at the denominator. So that is, since R is this guy, you just take it and cube it basically. So it's R squared plus Z squared to the power of 3 halves. All right, so this blue guy is R squared plus Z squared to the power of 3 over 2. Okay. Now I'm going to do the integral to find that BZ. All the constants will be factored outside. You got mu naught I R squared over 4 pi. And then the integral. Wait a minute, did you notice anything here? The integral is in terms of d phi. These don't contain d phi. These don't depend on phi at all, actually. And you guessed it, they're just going to pop outside. So you end up with R squared plus Z squared just leaving. And the integral couldn't be any simpler. You're integrating the ring. So you have to go, of course, take the bounds from 0 to 2 pi. That gets you 2 pi. It partially cancels that term. And out comes your magnetic field along the Z. Mu naught I R squared over 2 R squared plus Z squared to the power of 3 halves. I don't know, but this should feel familiar because we used it a little bit earlier. This little guy, we used it on the inductance question. I brought it in from hyperphysics, but I could have just written it down myself. It was on this problem here. There he is. It matches exactly the one that you see on the, I guess on the inlet. Okay, there you have it. So derived. And yeah, over here we just took Z to be 0 in this problem because we were approximating this green loop basically is going to be near the center, and it's all going to experience the magnetic field that you feel exactly on the axis, which is straight up. Not only that, but all its points are on the Z equals 0 position. There you go. So that's how you derive the finite ring here. Not finite ring, the ring of current along any point on the Z-axis of that ring. You put together a geometry argument and the Biot-Savart law, which I've converted this time to use the magnitude form of it. The magnitude form. Because I know where the magnetic field is going to go from symmetry. And whenever I know, I don't have to search for the direction from the cross product. I can omit the cross product. And just write about its size, basically. So the size is just this. What do you guys think? Thorough? Was it good?
Yeah, looks good.
Neo, any questions?
Yeah, I had a question. The one part that kind of confused me was how you got dBz equals dB cos theta.
Yes. So you see over here, if you break down dB into a component right now, the easiest way to describe this xy component is if I told you that it extends in the cylindrical r direction. That might make it more straightforward to understand why it's perpendicular to the z-axis, because RC is perpendicular to z in cylindrical
Yeah.
coordinates. Right. So if you use RC then, and that's the component that exits the z-axis, then there has to be one that actually is along it, right?
Yeah.
Okay, so what I'm saying is, if you have the hypotenuse, which is the total, you can always decompose it into this one, which is perpendicular to the z-axis, and the one that is along the z-axis. You can always do that decomposition. And you treat the situation like a right angle here. Right
That
angle
makes
triangle.
sense. So then that angle theta there is the same as the one at the top of the loop on the other side.
Yeah, and it's why is that? Because after we use the fact that this is pi, we said that this one has to be 90 minus theta. And if this is 90, which it is again, it's a radial, it's an RC line that extends out from the z-axis. So it has to be perpendicular. Then that leaves no room for that but to be theta. Yeah. So the common mistake, Neo, is that people drive this angle here and they call this one theta. But it's not. They do this a lot in the electric field. When you find the electric field of a charged ring, it doesn't work in this way. This is not 90, and these are actually opposite angles in the electric field version of this problem. But in the magnetic field version of this problem, the dB is perpendicular to the R. It has to be. Versus in the electric field version, this would be one of the contributions along this vector, and the other one would look like this. You see very different vectors for the electric field if you were doing that problem.
Okay.
That's my 2 cents. What do you guys think? Good?
Yeah.
Jeffrey and Alina, all good with that?
Yep.
Yep, all good.
Okay. I didn't address the square problem here. So you know how you found earlier the magnetic field of a finite wire segment, and it was this. Well, if you put them all together here, if you put your thumb along the eye and curl your fingers, you would see them again point out of the page here in the space of P and into the page here. You would see your fingers do this sort of thing. And this continues as you go around the actual loop over here. You can probably see what's going to happen here as I combine 4 finite segments here if I want to find again the magnetic field at P, right? They're all going in the same direction, and we can recycle the result that we just found for the one segment, okay? So at P, I'm going to have 4 overlapping segments of length L. Thankfully here, I've done the problem. So if the segment is of length L and the point P is directly away from its middle here, a distance d away, for you this distance would be d over 2. I want you to see that. Not d over 2, rather, if this is a square, you understand again that each of the sides is L. So if you're wondering about how far is point P from the center of each of these, it's just going to be L over 2, of course, if this is a pure square. Easy peasy lemon squeezy then to find again the magnetic field contribution from each one. So again, I would say here each wire, how much does it contribute, right? Well, bring in Mr. Formula from the left and recycle the result. You see, D represents now L over 2. It's the distance from the middle of the wire segment to the center of the square here. So I would go here and then replace the D, okay, with the length. I'm going to do it carefully here. Replace D with L over 2. Yeah, let's just say that this is L, like the small L. So D is equal to L over 2. Very nice. I need to change it in one more location, and I'm good to go. Right there. All right, so this is the B of each segment. And you can imagine here, from all segments, you just have to multiply this result by 4. Because all of them are aiming in the same direction when it comes to point P. So B total is 4 mu naught I L over, I guess here you can cancel a little bit. You get 2 pi L, 2 pi L, yes, root L squared over 4 plus L squared over 4, that's 2L squared over 4. And that can give you, if you push it a little bit more, that can cancel this 2. And that can cancel this L completely. Actually, yeah, you can cancel this L completely there. And then what do you got left? 4 mu naught I divided by, let's see, we said the 2 cancels. You have a root 2 at the bottom, a pi, an L, and then nothing else. Really, no, everything else is gone. Yeah. So, interesting again, use and recycling of the previous result. So you can find the magnetic field at the center of a square loop of length L. So see what I mean? Recycling, recycling, recycling. Whether it be an infinite loop result, sorry, not an infinite loop, an infinite wire result, or a circular loop, or a finite line segment, whatever magnetic fields you're given, you can always recycle them to find something new. What do you guys think about this?
It's okay.
Awesome. Okay, so I did all of that question. It was all bits of art. And I think that's a good place to close that recording as well. This was A, B, and C of that question. Wonderful.